Okay, so let's do a quick overview of quantum mechanics and try and summarize what we've learned to date. So to start us off, let me describe in words a physical experiment that you can perform in a laboratory, and we'll see how we've translated, how quantum mechanics translates this sort of experimental setup. The basic system we've been looking at, the spin-half system, is realized in our system of silver atoms, which have one valence electron. And what we've been doing is we've been saying that we want to take a bunch of silver atoms, all prepared the exact same way, and measure some property of them. So let's define a few terms. So we're looking at silver atoms. One silver atom is what we have been referring to as the system that we are looking at. Okay, the individual things that we measure are our system. They're all prepared the exact same way. So on this next page, what I'm going to do is I'm going to draw a sort of general schematic diagram of what we're doing. So the first thing we do is in our laboratory, we have some apparatus that prepares our system so that we can prepare it in the exact same way each time. And we'll see why this is important in a minute. So this is our preparation. Now, for the spin-half system with silver atoms, what does that preparation look like? Well, to get the silver atoms, we had an oven with an opening in it, so the beam of silver atoms could be heated up, vaporized, and a beam of atoms could come out. And then that beam of atoms was passed into a particular Stern-Gerlach analyzer, let's say S along Z, and then we selected spin up along the Z direction. Okay, so this is our preparation, right? By doing this, we've prepared a beam of silver atoms, and they are all prepared exactly the same way. They all have spin pointing up along the Z direction, right? So we could choose them to prepare them in any other way that we want, but this is just one example of what I mean by preparation. Okay, and then we want to measure some property of them. All right, so we pass this beam into our next piece of experimental apparatus in our lab, which measures some property of them, and the property. This is what we refer to as an observable. Anything that we can measure is an observable. And in quantum mechanics, we describe observables by operators. Right? So we've gotten used to labeling the experimental measurement apparatus with some observable O, some operator O. It's an operator because it's got a little hat on. Okay, now in quantum mechanics, the system is described by a state vector. It's a vector, and it's in this abstract complex vector space called Hilbert space. So the operators we've generally referred to as O, the state vectors as psi. So after our preparation, we have our system in a state psi, and we measure some observable O. Right over here, in this example, the state psi is equal to the state spin up along the Z direction. And then we feed it into, let's say, some other apparatus. Let's say we want to measure spin along the X direction. Okay, so I perform an experiment to do so. So this is my apparatus, and I record the measurement of that property of each atom. Right. So this is where quantum mechanics. This is the next place where we have a big difference with classical mechanics. The measurement of that property of each atom, I don't know ahead of time. I can't predict what I'm going to measure in general, given an arbitrary input state. All I know are possible outcomes. And how do I know those outcomes? Well, in quantum mechanics, the role of the operator is to tell me what are the possible outcomes of my experiment? And it tells me that via its eigenvalue equation, which says that the operator operating on some special states, which I'm going to call lambda O, and there are a number of possible states, which I label I, and they result in a particular number times the same state lambda I. Okay. Given an operator, I can solve this equation to find what these states are, which are called eigenstates, and what these values are, which are called eigenvalues. Okay. Or alternatively, if I conduct an experiment and measure all the possible outcomes, then I can use this equation to figure out what the operator is corresponding to the observable I just measured. So sometimes we do it one way, sometimes we do it the other way around. So what do I actually, in the real world, what do I physically record? I physically record the eigenvalues, or a particular eigenvalue. I don't record all of them. When I make a single measurement, I obtain one of the possible eigenvalues. Lambda 0, lambda 1, lambda 2, and so on. I measure one of those. And after I do so, the system is now in the state corresponding to that. To that eigenvalue. Okay. So a single measurement gives me a single result, which is one of these lambda i's, and the probability that I obtain that result, lambda I, given the input state psi, is equal to the square modulus of the final state, which is lambda I0, the inner product of that with the initial state psi. And it's the square modulus of that squared. Okay. So I get the probability that I get this measurement is given by the square modulus of the initial with the final state. Okay. I repeat this measurement a million times. Each time I'm going to get I will get a different outcome with some probability, right? This is probabilistic, so I might get just like tossing a coin. I might get a couple of heads in a row or tails in a row, right? So I may get the same result more than once in a row, but what I get is random and is governed by these probabilities. Right? At the end of all of my measurements, I take the average of those values, and the average is called the expectation value in quantum mechanics. And the expectation value is given by the inner product of the input state psi with the operator O acting on the input state psi. Okay. And I can take the standard deviation as well, which is called the uncertainty delta O, which is the square root of the modulus of the expectation value of O squared minus the expectation value of O squared. Sounds the same when you say it in words, but it's different. Okay, so where the expected value of O squared is just, instead of O, I have O squared in here. So I need that as well. Okay. Okay, so now, so far this is abstract somewhat. The question is, how do I calculate this? And to calculate it, I need to write these various states in a certain basis. So the first thing you do is select a basis. We went through this exercise in class a few weeks ago where I asked you how you describe a vector to someone. right, you need some numbers, and to do that, the first thing you need to specify is your basis, right, your axes, if you like. Now, there are a choice of bases, right? Experimentally, there are several possible observables for each system, right? For example, I could choose to measure the spin along the x direction for my silver atom, or the y direction, or the z direction, or the total spin, or the energy, and so on. So I've got a whole bunch of possible observables that I could do. So I could set up my experiment to, let's say, measure observable A, or observable B, or observable C, and so on, right? And I could feed my atoms that are all prepared in the same state. I could just pick up this box in my lab and feed my atoms into this box and measure this property, or feed them into this box and measure this property, and so on. And each time I'm going to get, my range of possible outcomes. Right? I forgot to fill in here, of course, the range of possible outcomes in this example. You've got the eigenvalues are plus h bar over 2 and minus h bar over 2, and the output states are plus x and minus x. Here we're just going to stick with calling them lambda 0a, lambda 1a, and so on. Here it's lambda 0b, lambda 1b, lambda 0c, lambda 1c, and so on. And then let's call the states. Let's call the states this, and then the corresponding eigenvalues are just lambda 0a, lambda 1a, and so on. The things that you actually measure. So you've got a bunch of possible choices of observables to measure in your laboratory. Right? Now, what observables do is the operators O, they give you the possible outcomes of measuring that observable, which are the eigenvalues, but they also give you a basis, a set of basis vectors, which are the eigenstates. So each of these gives a different basis. Okay. And I can, just like with ordinary vectors and different coordinate systems, I can write the same vector as a linear combination of basis vectors in whatever basis I choose. Right? So I can expand my input state as a sum of some coefficients times the particular eigenstates of a particular basis. Right? So this is called expanding psi in the A basis, the basis corresponding to observable OA. Right? I could also write it as the sum over bi lambda ib. Okay, so this would be expanding it in the B basis. Okay, so, and I could do the same for C. So I could write this exact same state in several different ways. And we've seen how you can do that. Right? For example, the eigenstate of spin in the z direction, this in the z basis is itself, right? It is one of its own basis vectors, right? So this is in the z basis. In the x basis, this is equal to 1 over the square root of 2 of up along x plus I down along x. And in the y basis, it's equal to 1 over the square root of 2 of up along y plus down along y. Okay, I figured this out because through cyclic permutation of the formulas given in the book, right? Because we know that in the x basis, the x vectors are the vectors 1, 0 and 0, 1, which means that x has become z, and that means z has the same form as y does in the z basis, which has the complex, the imaginary coefficient here. So while I'm mentioning the vector notation, this vector notation here is 1, 0. Here it's 1 over the square root of 2, 1i, and here it's 1 over the square root of 2, 1, 1. Okay, these are all the same vector in different coordinate systems, different bases. Right. The operators themselves can be written in particular bases. Right? How do we write a vector? So this is how we write vectors in various bases. How do you write operators in a basis? Let's pick the A basis from up here, then the if you take the operator, and let's take A for example, the operator A, that in the A basis is simply the matrix element you just simply use the matrix elements of this operator, which is the sandwiching of the operator between the basis vectors. So this is the matrix element corresponding to the ith column and the jth row. So this, if you calculate this gives you a number that you put here in the matrix. Right? And by changing I and j, you can generate the whole matrix here. Okay. So this is called a matrix element for obvious reasons. And this gives you OA in the A basis. Right. If you want OA in the B basis, you calculate the matrix made up of matrix elements got by sandwiching the operator OA in between the eigenstates of the B basis. If you want the operator B in the A basis, then you calculate the matrix elements that you get by sandwiching the operator OB between eigenstates of the A basis, and so on. Okay, so we now know how to get states in a particular basis. We can often to help find vectors in a basis, or in general to help find vectors, it's useful to make sure, or to remember that quantum state vectors are normalized, first of all, so any state has to always obey this relation. And basis vectors are orthonormal. So if you take the inner product of two basis vectors of the same basis, two different ones, then you get 1 if they're the same, or 0 if they're different. They are also complete, which just means that there's enough of them to expand any vector in that basis. And that means that the sum over I of the inner product of, the outer product of two eigenstates that are the same eigenstate, and you add them up, they're equal to 1. And these things here are projection operators, which I will come back to in a minute. So this says that the sum of the projection operators should give you the identity matrix. Okay, now when we go back to the physical quantities that we can calculate, again, it helps to divide things up into things that exist in real life in our laboratory and things that exist in the abstract Hilbert space of quantum mechanics. The Hilbert space, remember, is the complex vector space. So, and the things that exist in real life are things we can measure or observe or calculate from measurements, right? And they are the eigenstates of a particular operator, the probabilities of measuring a particular outcome given an input state, and the expectation values of observables and their uncertainties. So those are the things that we've encountered so far that are real. Right? So everything in this column must be a real number. Then there are things over here like quantum states, like basis states, like operators, like projection operators, for example, that only exist in this Hilbert space. So these are not things we can observe. I should put a little hat on here. Okay. So we know how to get these observables. We just measure our quantum system. How do we calculate these things if we're given these abstract states? Well, to calculate the probability of measuring a particular observable given an input state, to calculate this inner product, you need to write them in the same basis, right? And usually that means writing the input state in the basis corresponding to that operator A. So write psi in as some linear combination of these states here, because then you can take inner products with these states because they're always either 1 or 0. Right. And to calculate the expectation value, which is always the operator sandwiched between the input states, then you either write O in the same basis as psi in is written in. So for example, if you've written psi in as the sum over I, AI, lambda I, A, then you need to write the operator O in the OA basis. Or your other option is to, let's call this OB, or you need to rewrite psi in the OB basis. And usually it's this first one that you're going to do, but it depends. It depends on the exact problem. Okay. We can picture this abstract vector space, and we can picture what goes on in the abstract vector space when you make a measurement. When you take your input state and you make a measurement, and you measure, let's say you measure lambda I, the eigenvalue, the ith eigenvalue of observable OA, then what's going on is, if you write psi in the A basis, okay, so you have axes corresponding to the So let's say this is lambda 0, this is lambda 1a. If there are more possible outcomes, then there are more orthogonal axes. We were used to dealing with two-dimensional axes in most of the examples we've encountered. The vector psi is some vector in that space. Okay, so this is the input. And the output is going to be one of these basis vectors. So there are two, the way I've drawn it here, there are two possible basis vectors. This is lambda I A, and this is lambda 0a, and this is lambda 1a. Okay, and suppose to do the calculation, you have to write psi in the OA basis. So unless, again, let's just assume there are two possible states. So this is just A0 lambda 0a plus A1 lambda 1a. Okay, then a measurement takes you from this state going in to one of these two states coming out. Right. So that corresponds to, firstly, projection of this state onto the x-axis. Right. So to go down this way, we perform a projection operation on psi, which takes you down to here. Now this vector here is, you're projecting out just the bit of the vector, the component along this direction, which is this bit here. So this gives you A0 lambda 0a. Okay, and then you shrink this down to get your final state. So all in all, you can write your final state, the final outcome of a measurement is this projection of psi divided by its normalization, which you can show is equal to the matrix element of P with psi. It's the modulus of that. Okay. Sorry, it is the square root of the modulus of that. So that's what it looks like. That's what measurement mathematically corresponds to in our abstract Hilbert space. The projection operator also gives us a way of calculating what happens if you feed two beams into, or two different states into an experiment. Psi1 and Psi2, and make a particular observation. Then the state that you get as an output is going to be the projection operator corresponding to that output operating on psi1 plus the probability, the projection operator acting on psi2 divided by the square root of the square modulus of this, which I won't write down here. Okay, now a quick word about these coefficients here when you expand a state in a particular basis. Let's see how they're related to probabilities. Well, to show how this expansion helps when calculating the probabilities, let's plug it in. Let's say we are interested in calculating the probability of measuring lambda IA given an input state. An input state psi. This is the square modulus of lambda IA with the input state psi, which from here is the ket, or is the sum of over j, aj lambda ja, where we have to be careful to use a different label for this sum as the label here because they are in general different things. And oh, sorry, I don't know why I'm using the bra version of this. This is the Ket version. Well, this state here can be moved inside, and we can take the inner product of this with this, and the inner product of that with that just gives delta ij, right? It's 0 unless I is equal to j, in which case it's 1. That's just the orthonormality of the basis states. And so every term in the sum is 0 except the one where j is equal to I, so we're just left with ai squared, which is ai star ai. Okay, and these coefficients are therefore called probability amplitudes. Okay, so if you know this expansion, then the probability of measuring any of the basis states or any of the eigenvalues corresponding to the basis states in this expansion, you just take the coefficient and take its complex conjugate multiplied by itself. Okay. Also, remember that in this expansion, we can always choose the very first coefficient to be real as well. That's also useful to bear in mind. Going back to the picture I have here, where I said there were several possible observables for each system. Okay, so one way to think about this is that each observable, what the observables give us is it gives us a number of real things that we can measure in the laboratory, the eigenvalues, and then it gives us a bunch of things in our abstract Hilbert space. Right. Both of these come from the eigenvalue equation. Right. If you take another operator OB, then it comes with its own set of eigenvalues and its own set of eigenstates, and so on. Right. So that's what operators corresponding to observables give you. I forgot to mention that operators corresponding to observables have to give real eigenvalues, which means they are Hermitian operators. If I have an arbitrary state psi, I can expand it either in this basis or this basis or any other basis corresponding to a particular observable. So you can think of this, each quantum state psi comes along with a bag of numbers, ai, which are the numbers I put in front of these basis states and add up to give me the state. It also comes with another bag of numbers, bi, which I can put in front of these basis states to expand this state in this basis, and so on. Right. So you think of any arbitrary quantum state comes with its own set of bags, one bag for each observable, and each bag contains a bunch of probability amplitudes. And those probability amplitudes tell me what the probability is of measuring the corresponding eigenvalue of that observable. The final thing I want to mention is that the solution to the Schrödinger equation, which tells us how a particular state varies in time and is the equation of motion in quantum mechanics, the solution to this is given by the state at a time t is equal to what we do is if we take the state at time t equal to 0, the state psi at time t is equal to e to the minus I h hat over h bar times t times the state at time t equals 0. This just comes from solving this equation. Okay. H is the operator, the Hamiltonian operator corresponding to energy, the observable energy. Now, you can calculate this if you expand psi of 0 in the energy basis. So let's call it this lambda. So AI, let's call it CI, since the book does that. CI times EI, where EI are the energy eigenstates corresponding to the operator H. Right, which again, it gives me a basis, so I can expand any vector as a function of this basis. Then this solution here to the time-dependent Schrödinger equation means that the operator h hat operates on each of these, and the result of this is to give me e to the minus. The eigenvalue corresponding to this is e sub I. So this gives me a recipe to find the state at a time t given the state at a time 0. I take the state at a time 0 and I expand it in the energy basis. I then write the state at time t as that same expansion, except in front of each term I write e to the minus I EIT over h bar, where EI is the eigenvalue that corresponds to the particular eigenstate. So the final thing is that there are operators that commute and operators that don't. If they commute, if two operators commute, then the order of their product doesn't matter. Oops. And we've already seen one importance of this fact, or a couple of things that are important. If two operators commute, then they share the same eigenstates. Okay. They do not share the same eigenvalues. That would make them the same operator, but they share the same eigenstates. Okay, so for example, the Hamiltonian for the spin half system in a uniform field, magnetic field in the z direction, its eigenstates are the same as those of the spin operator in the z direction. But the eigenvalues are different. The energies are plus or minus h bar omega over 2, omega 0, and the spins are plus or minus h bar over 2. But the eigenstates are the same. Okay. And this has importance for time evolution because the energy eigenstates are stationary states, which means that if either the input or output states are energy eigenvalues, then the probability and the expectation value doesn't depend on time. However, if the both input and output states are not energy eigenstates, then the probability and expectation values in general will depend on time.